Hello students, this video is a continuation of a previous video on a basic example of the dot product. If you haven't seen that video, then I recommend that you take a look at it, or if you already are familiar with the dot product or scalar product, you just look at a quick review of what I've done here, and you see that u dot w doesn't make any sense. We can't put these together, okay, because these are not compatible dimensions for these vectors. U is a 3 vector and W is a 2 vector, and you'd run out of components here. All right, now what I want to do in this remainder of this video is to offer you a perspective, more of a, I suppose, linear algebra perspective. This will help with coming to terms with matrix multiplication and other operations that you'll encounter in linear algebra. So I'm going to think of U and V as column vectors from now on, or you could think of these as like 3x1 matrices if you'd like. That's perfectly valid. And we're going to compute the dot product of U and V, so U dot V. But whereas I just took U dot V and I just multiplied them component by component, you could think of U dot V as from another perspective, and that would be U transpose. This little t means transpose. So U transpose multiplied by V. So let me show you what U transpose looks like. Here's U, it's a 3x1 column vector, and V is a 3x1 column vector. U transpose is U just toppled over, just flipped down. Now you got to be careful how you flip it. You don't flip it to the right, so it's -5 to -3. You flip it to the left and it becomes -3 to -5. So now when you multiply these two vectors, you're going to see that you're going to multiply a 1x3 vector here, U transpose, by a 3x1 vector, V. And I'll go through why that's important in a moment. So here's what the operation looks like. Here's U transpose, it's 1x3, and here's V, it's 3x1. And we perform the multiplication just as we did before. We take the -3, the 2, and the -5, which are the components of U, and then we multiply them by the components of V, 9, 4, -4, and then we add them all together, and of course we got 1. Same result I got before. Now here, U is a 1x3 vector, and V is a 3x1 vector. And here's a nice little mnemonic. You notice that these 3's match up. Right, they coincide with each other when you write the dimensions next to each other. And so we could think of those as collapsing, and we get a 1x1 result. 1 here, which is a 1 which has dimension, any scalar has dimension 1x1, so that's a scalar. Likewise, if we were to take V dot U, we would have V transpose U. So we topple V over, remember, to the left, so that becomes 9, 4, -4. Then we multiply the components of this 1x3 vector, 9, 4, -4, and we multiply by the vector V, and we get the same result. So that tells us that the dot product is commutative. U dot V equals V dot U, or U transpose V equals V transpose U. So whenever you see either of these notations, U dot V or U transpose V, they mean the same thing, and they are commutative. All right, so that offers you a slightly different perspective on the dot product. Good luck.